Welcome to today's interactive training webinar on the latest innovations in organic solar PV cells, an online lesson. This is part of a webinar series run by the accredited European Energy Centre, EEC. The EEC has been active for 40 years as an independent professional body for the renewable energy sector, providing educational activities in Europe, the United States of America, and globally. My name is Paolo Buoni. I'm a director of the EEC. I'm based at the European Energy Centre offices in Edinburgh, United Kingdom. I've been in charge of helping the United Nations Environment Programme, UNEP, launch the Green New Deal, and I'm now in charge of the organisation of global classroom and distance learning renewable energy courses, available in Europe, in the United States. Information is on the EEC website, you can see on the slide. Here with me, I have connected live from the University of Chicago, Alexander Schneider, University of Chicago, Lupin Research Group, who is currently researching the synthesis of organic semiconducting polymers for photovoltaic applications. But before we start this exciting webinar, I'd like to share with you some information about the EEC. The European Energy Centre is an accredited centre offering qualifications and training courses on a variety of renewable energy and energy efficiency topics, with classroom and distance learning. In fact, we now have 105 countries connected live globally to the training learning online platform as we speak. We work with the United Nations Environment Programme and leading lecturers of major universities promoting best practice in renewable energy and energy efficiency. We do this through the training courses and the conferences. Certificates achieved by participants on the courses are internationally recognized. This is the Galileo Master Certificate, and it is provided to participants who pass the exam at the end of each course, both classroom or distance learning. We also run online e-training courses on an innovative distance learning platform with live tutorials and online videos taken live from the classroom courses held at the UK universities. All courses are designed for people coming from all backgrounds, also intending to start a career in the renewable energy field or expanding their field of knowledge within the renewable energy sector. We also run the Global Professional Membership Program, Energy CPD, which gives professionals and students the opportunity to gain recognition and status within the industry. This is through professional development and by becoming members of the EEC. If you wish to register for any of the courses, you can visit www.euenergycentre.org for classroom courses or www.academy-eec.co.uk for distance learning courses. Now back to the webinar. So throughout the webinar, participants can ask questions by writing those on the chat box and click on send. The questions will then be read out by my colleague Scott at the end of this webinar. Also, if you'd like us to send you the certificate of participation for this webinar, which you may need for your CPD or energy CPD hours, please email us on training@euenergycentre.org, stating your full name and the correct code, which will be given out later throughout this training webinar. When contacting us, you'll be asked for the code in order to receive the certificate of participation. Now I'll pass over to Alexander Schneider, University of Chicago, who will present on today's webinar. Over to you, Alex.
Thank you for the kind introduction, Paolo. It is an honor to present this webinar on polymer solar cells to the members of your organization. So as mentioned, my name is Alex Schneider, and I am a research assistant in the Looping U research group at the University of Chicago. Our group focuses on the synthesis of organic materials and organic polymers for use in electronic applications. We are best known for We are best known for our work in polymer solar cells and related technologies. You can find out more information about our group at loopingu.uchicago.edu, though please note that this site is currently undergoing an update, so yes. All right, this webinar will be divided into 4 sections. Initially, I will talk about an introduction to solar cells in general and polymers and how the two interact. Then I will get to talking about the first generations of polymer solar cell materials. Later I will move on to the more modern polymer solar cell materials, and finally I will give us some brief conclusions on the field. Please note that this topic may be a bit more technical than some of you might be used to, and that's just where this field currently is right now. This is still very much in the realm of laboratory work. All right, so to the left of this slide, you can see a chart that most of you are probably already familiar with. This is the current best research cell efficiencies. This is provided by the U.S. Department of Energy, the National Renewable Energy Laboratory, so these are certified cell efficiencies. Now you can see here on this slide the sort of 3 generations that solar cells have gone through. So the first generation of material, which is by far the vast majority of the material available commercially at this point, is based on crystalline silicon. So that's the blue traces on the NREL graph. And these get about 15 to 20% PCE, and they're very well established, so they make up the vast majority of commercial solar cells. Some disadvantages of these technologies is that a high amount of very high purity silicon is required. And that's expensive in and of itself, and it also exposes the producers to they're significantly exposed to the global price of silicon in the marketplace overall. So the second generation of solar cell materials is based on inorganic thin films. So these have similar PCEs to the crystalline silicon thin films. However, they use a much smaller amount of material. So they typically use a film of only about 100 nanometers thick. Now, the downside to these materials are they use rare and in some cases toxic elements like cadmium, tellurium, indium, selenium, gallium. So these materials are quite rare. So even though there's not a lot that are used in the production of solar cells, they're intrinsically using difficult to obtain elements. So now, but despite that, these second generation technologies are just beginning to enter the marketplace. So we'll see how they end up working out. Now the third generation of solar cell technologies is sort of a catch-all generation for all sorts of new technologies that are in the laboratory right now but might eventually find their way onto commercial optimization in the future. So the third generation technology that I work on is polymer thin films. So now, like the inorganic thin films, these use just a small amount of material, so also 100 nanometers. And like the inorganic thin films, they're flexible. However, unlike the inorganic materials, these are carbon-based, which is a couple of advantages. By itself, carbon is more common on Earth than all these rare elements, so that that gives us the possibility that potentially these could be cheaper in the long run because they're using intrinsically more common materials. In addition to that, polymers have an advantage, a very big advantage, in that they are soluble in organic solvents, so that makes the fabrication process of solar cells based on them very simple. you can simply dissolve them in organic solvents and coat them onto an electrode. So essentially you're producing a solar cell just by coating a layer of solar cell paint onto an appropriate paper. Now, unfortunately, these do have drawbacks, which have made it so that they're still within the realm of the laboratory right now. They're relatively inefficient, so we've just recently broken the 10% PCE barrier. They're expensive, so even though in the long run they have the potential to come down in price, I think a lot more than the inorganic thin films, right now they are currently expensive, and that's made commercial optimization hard. And the stability of devices is known to be a proper issue, common issue, in that some parts of these devices are attacked by air and moisture, which requires them to be encapsulated to have in order to live similar lifetimes to what consumers would expect. All right, so now that you've got some idea as to what these solar cells are based off of, I'd like to give a brief overview of what exactly is a polymer. What are we making these things out of? So let's see. And so how can these things generate electricity at all as well? So polymers, in contrast to small molecules. So small molecules is what we usually work with as organic chemists. So these have definite structures. So ethylene has a formula of C2H4 and acetylene has a formula of C2H2. Now polymers do not have a definite, well-defined structure. They instead have repeating units that may repeat a variable number of times. So polyethylene has the formula C2H4 repeated some number of times, and polyacetylene has the formula C2H2 repeated some number of times. Now, these have been known for over 100 years, and these have been polymers have been commercially important since about the 40s, but until quite recently they were the domain of more material scientists than actual electronic engineers. So stuff like polyethylene is more known as a packing material than it's not electronically interesting at all. And similar polymers, other polymers are construction materials or textiles. It was only in 1977 when Shirakawa, McDermid, and Heeger developed polyacetylene, which conducted electricity, that polymers could be used as electronic materials. And you can clearly see the difference. I have up on the screen pictures of polyethylene and polyacetylene. And polyethylene, we're all familiar with. It's just the plastic that goes in plastic bags. And polyacetylene, you can see in the provided image, basically looks like a piece of aluminum foil almost. It's clearly much different than the polyethylene, even though they're both polymers. Now, however, despite appearing metallic, these polymers retain some of the important advantages of normal polymers, such as flexibility and processability, along with gaining these electronic properties. Now this work was very important. It eventually won these three professors, Shirakawa, McDermid, and Heeger, the Nobel Prize, which the three of them shared in the year 2000. And that was very well deserved. So these materials are beginning to obtain actual economic applications. So some flat screen TVs and other device like phones and other displays are beginning to use conducting polymers in their design. So now, how exactly are these useful? What makes them useful as semiconductor? What makes them conducting exactly? So, what electrical engineers and engineers are caring about in materials what divides them into three classes of insulators and semiconductors and metals is the band gap. So electrons that hold together all materials can only occupy certain regions of space. So all materials have a valence band where the electrons start out and a conduction band where the electrons can move into. And the distance between those two spaces is an intrinsic property of the material known as the band gap, which will determine whether the material is an insulator, a semiconductor, or a metal. So this is actually is quite similar to people on a train. So electrons can only occupy certain states, much like people boarding a train can only go on certain seats. And so insulator is much like people on a filled train car. Nobody can move anywhere, even if they want to, because there's nowhere else for them to go. While metals are like people in an unfilled train car that if you wanted to, you can get up and move around and move about and travel. Now, semiconductors are kind of a combination of these two. They're much like people in a filled train car that can leave the train car and go to a separate train car and then which is empty, and then they can move and go about their business. So anyway, that silly little analogy aside, what we care about is the energy that's required to move electrons from this filled area to this empty area, and that takes a certain amount of energy. And in solar cells, that energy is provided by sunlight. So to the left, you can see a chart of the solar spectrum. So this is from the National Renewable Energy Laboratory, and this shows the amount of energy emitted by the sun which reaches the Earth at various energy levels. So, and like I mentioned before, each semiconductor has an intrinsic band gap, which is at that point an electron can move from the valence band to the conduction band. So when the band gap of the semiconductor overlaps with the band gap of when the band gap of the semiconductor overlaps with the spectrum, with the energy provided by the sun, an electron can be promoted and go to an empty orbital and move around, and once it can move around, it can generate electricity, which ultimately is what we want from the solar cell. That's what provides the power, these moving electrons, which it all begins from the sunlight provided. But it's very important to match the energy your solar cell requires with the energy that the sun outputs, because any part of the solar spectrum that the semiconductor does not absorb is going to be wasted and be of no use. All right, so once we have a candidate material that absorbs over the desired region of the solar spectrum, we'd like to get energy out of it. And how do we do that? So we'll hook our solar cell up to simulated light and provide it with a voltage, and that will give us a JV curve, such as shown at the left. So as you can see, this gives us a couple of factors. The most important factor that we can derive from this curve is the power conversion efficiency. I mentioned that early on in my talk, and this is the most important value given by a solar cell. So the power conversion efficiency is the output electrical power that the solar cell generates divided by the input power that the sun provides via light. So this is the most important quality of the solar cell overall, and what we compare different solar cells against each other to. Now, we can divide power conversion efficiency into several factors. So the open circuit voltage is the voltage provided by the solar cell. That's somewhat similar to how much energy each electron is providing. At the opposite end, the short circuit current is the current provided by the cell. That's basically how many electrons our solar cell is providing, which is in turn related to, how much sunlight is absorbed, how many photons from the sun are absorbed. And finally, we have the fill factor, which is sort of catch-all term, which is generally how well our cell is put together. It's got a lot of different properties. One of the major ones is how well the different layers of our cell fit together. If there's a lot of resistance between them, the fill factor will be low. Now, we want all these parameters to be as high as possible, and that's a bit difficult because there's some intrinsic trade-off in some of them. So most of the things we do to raise VOC will lower JSC and vice versa. However, most solar cells that we've made, we can find a happy medium where we get a decent amount of PCE out from the cell. All right, so I mentioned fill factor is related to the resistance of various parts of the cell and how that relates to the overall quality, how well each piece of the cells fit together. Now, what are those different pieces of the solar cell? Are here. So you can see a solar cell is composed of, in this silly little cartoon, you can see a solar cell is composed of two electrodes, a transparent electrode at one end that light can shine through, and a metal electrode on another end. And then there will be some conducting material in between those electrodes and the active region, and the active region will be composed of a donor semiconductor that will give electrons and an acceptor semiconductor which will accept electrons. Now, the way this will operate, if you can look to the top right, is as light will travel through the transparent electrode and will reach the donor region of the solar cell. At that point, as I described earlier, if the light that hits the cell matches the semiconductor band gap of the solar cell material, it will promote an electron from the valence band, where it begins, to the conduction band, where it is free to move around, as I described previously. Now, once the electron is in the conduction band, it's free to move around, and in doing so, it will eventually reach the interface between the donor and acceptor region. Once it does that, it can transfer to the acceptor region, and from there it will move through the acceptor region and eventually reach the electrode. And this traveling electrode is what ultimately provides all sorts of solar cells, not organic solar cells necessarily, but all sorts of solar cells with an electric current. All right? And a similar process occurs in the donor region, in that holes are transferred through the donor region to the transparent electrode. All right. Now, these sorts of bilayer devices that are composed of a transparent electrode followed by a region of donor, a region of acceptor, and another electrode are common in inorganic solar cells and They're both silicon and thin film technologies. And the first organic solar cell also developed was a bilayer solar cell as well. So this bilayer device was developed by C.W. Tang in 1986, and it was composed of a organic donor and organic acceptor, similar to silicon, just one layer of each on top of each other. However, it was quickly found that this had a problem in that, unlike silicon, the electrons are not as mobile in organic materials as they are in inorganic materials. So the problem was that the region of contact where the donor and acceptor touch each other is not very large. And that's not a huge problem if your electrons are free to move very easily. But in an organic material where they're not quite so free to move easily, this is a problem because not all electrons will eventually find their way to the interfacial region. And if they don't reach the interfacial region, they cannot move to the other electrodes and generate charges. So this was a very large problem, which was shortly fixed with the introduction of a bulk heterojunction architecture. So this is a completely unique solar cell design to organic materials. It has no real analog in the inorganic world. And in this case, essentially what we're doing is just mixing everything together, our p-type material and our n-type material. And we're just making a coating of this, and spontaneously the p-type materials and the n-type materials will aggregate into their own separate regions of space. And this is very useful because now, as if you'll take a look at this cartoon compared to the last cartoon, there's a lot more interface between the red region and the blue region in the organic solar cells versus in the bulk heterojunction versus the bilayer device. Now, and this enables organic solar cells to overcome their limitation versus inorganic solar cells with regard to the ability of electrons to move around. And what's really great about this is we don't have to do anything to develop this. Just by mixing everything together and coating it on the proper surface, it spontaneously arises in this structure. And that's one of the main regions, that's one of the main reasons that makes organic solar cells as powerful as they are, in that they're able to spontaneously form this perfect organization for generating charges from light. Now, in making this too, this is also useful because the process of making this is just taking a coating of P and N-type material mixed together and coating it on the proper substrate is a much less expensive way of making solar cells than the various ways that inorganic chemists use to make silicon or gallium arsenide or what have you solar cells. So this can essentially be made, this is basically like a sort of paint, and we're really just painting solar cells. So that's really powerful in that it would cut away much of the really expensive production costs that are involved with other solar cell material. You could essentially just print off solar cells and have a working solar cell just coming out of your printer almost. All right, and now below the cartoon you can see several examples of different P-type donor materials that were common about 10 years ago, and these were a number of materials with lots of different band gaps and lots of different solubilities in organic solvents. So they had very different properties, but similar efficiencies. So it's quite impressive, actually, that all these wide variety of different architectures are able to spontaneously aggregate into these structures, and no matter what different material we start with, we end up getting this bulk heterojunction structure, which forms a solar cell and can absorb light and generate electricity. Now, ultimately, just a single one of these structures would emerge victorious, and that was the structure of P3HT that's shown at the upper left. And in 2005, Professor Yang at UCLA made a polymer with P3HT and acceptor material that achieved an efficiency of 4.4% PCE. So this was a record at the time, and this sort of cemented P3HT as the most important standard for polymer solar cells at that time. This original paper the Yang group had on the subject has at this point been cited over 3,500 times. And one of the advantages of this was the very simple structure of P3HT and PCBM, which made synthesis easy, and for such a simple structure, it was quite powerful to generate 4.4% PCE. And this has been worked on by many groups since then, and the PCE of P3HT-based solar cells are still improving. However, it is still quite low compared to other technologies. So one big problem that these solar cells had was the band gap of P3HT is quite wide. So it takes about 600 nanometer light to excite P3HT from the excite an electron in P3HT from the valence band to the conduction band. And if you don't mind, I'm just going to go back to the solar spectrum, and you can see so everything greater than 600 on the solar spectrum graph to the left is not absorbed by P3HT. So that's a very bad limitation. P3HT loses most of the solar spectrum. It just does not absorb it. And everything 600 and lower energy, so 600 and higher wavelength, is just completely lost by the cell. So this was seen as a major limiting factor, a major problem in these solar cell devices produced by the Yang group. And our group at UChicago and other groups elsewhere attempted to take care of this problem by making lower bandgap material. So PTB7, developed in our group in 2009, is a lower band gap material. So this absorbs at about 750 and 750 nanometer light and everything higher than that. And so this is able to absorb much more light. And so that problem solved. Luckily, it turns out that we were able to get higher PCE out of PTB7 than we were able to get from P3HT. And so we increased the PCE of solar cells from the P3HT of about 4.4 all the way to 7.4 in comparing PTB7 to P3HT. And at the time, this was the highest PSC, the highest PCE for a polymer solar cell that was known at the time. So this was a very, very big jump in efficiency and very well regarded in the literature. And as you can see, we accomplished this by changing up the structure. So P3HT is, going back, is a simple polymer. It's just got one repeating unit of diethene, and PTB7 is more complex. And what we're able to do with that is we're able to engineer it more efficiently so we can control its properties much better, like we were able to lower the band gap in comparison to P3HT and absorb more light. And we can modify a number of other properties similar to that. So, excuse me. So as you can see, this is accomplished by instead of using a simple molecule like P3HT, this is made by a copolymer of two different individual monomers alternating against each other. So PTB7 is created with the polymerization of the dimethyphene unit, TT, over in the lower left corner, with the benzodiazepine unit, BDT, in the one from the right on the upper row. So now, and you can see some test devices shown here. So in any case, let's see. I'm sorry, a moment. So by moving from a simple structure to a more complex structure in PTB7, we were able to modify these individual subunits individually to get whatever properties we want for our final polymer. And so you can see, again, on this page, there's a whole library of different monomers that we can combine to make polymers. And I spend most of my time working on new monomers, trying to expand on this library to generate more structures that we can use to make a wider variety of polymers. And by mixing and matching these individual units as we see fit, we come up with a wide variety of polymers to ultimately use in solar cell devices. All right. Now, once we have a library of different solar cell polymers, we can combine them in various ways. So there's one more thing I'd like to bring up about polymer solar cells, and that's the use of multi-junction solar cells. So these are well known in the inorganic literature, in that what you can do with these cells are you can combine them and just stack them one on top of another so that in one solar cell you have multiple semiconductors, and you can see on the solar cell graph here, so this device from the National Renewable Energy Laboratory, the different parts of the multi-junction solar cell absorb different regions of the spectrum, and so they're able to utilize much more of the solar spectrum by moving to this multi-junction architecture. So this is very useful for solar cells. However, it has a drawback in that it takes a lot of engineering work to generate these multi-junction solar cells, and that adds to the cost. So even though these multi-junction solar cells are incredibly efficient, when you add the cost of engineering them together, you might as well just buy more simple solar cells that are less efficient than buy this, one efficient multi-junction cell. The only cases you would want to move away from that currently are if your space is very limited, or well, that's the main reason. If cost isn't a concern and space is limited, you would want to use a multi-junction solar cell, in which case you'd get very high efficiency. So this has a analog in the organic solar cell community as well. So tandem solar cells combine two or more components, just like multi-junction solar cells, and they increase PCE at the cost of greater fabrication difficulty. So just like in the inorganic community, that they tandem cells can stack different donor polymers together to make a higher efficiency device than either of the individual cells by themselves. However, that's a bit of a problem for organic solar cells, because adding to the fabrication difficulty of having to produce a tandem solar cell sort of counteracts one of the major advantages of organic solar cells, in that they're very simple to fabricate, and tandem solar cells, even made of organic material, are not simple to fabricate. However, a technology that's recently gotten a lot of attention is the use of a ternary cell, which is made similar to the binary cell, just by combining a different number of semiconductors all in one, and all in one solution, and just spin coating it, like just painting it just in the exact same way we made the binary solar cell. We make a ternary solar cell which has multiple different semiconductors making it up. However, and so these ternary cells are able to get increased efficiency compared to the binary cells, just like multi-junction inorganic solar cells. However, unlike multi-junction inorganic solar cells or tandem organic solar cells, these are created the exact same way as binary solar cells, and so retain the ease of fabrication that solar cells are well known for, and which is one of their selling points, while being able to incorporate multiple semiconductors within them, which in other technologies takes a lot of engineering work. And for in organic solar cells, we can do that without having to do all that engineering work. It just spontaneously occurs due to the nature of the organic materials that we use. However, I'd like to point out that these ternary solar cells are very new, and so they're not fully researched yet. But I believe these can be one of the strongest selling points of solar cells in the future. Once the work is done to find out what different materials work well together and get the basic science figured out. And so yeah, these ternary systems just don't have any sort of these ternary systems don't have any analog in the inorganic world. So this is a very powerful selling point of them. All right, sorry, I just completely rushed through that faster than I realized I was going through. But in any case, in conclusion, a study of polymer solar cells is a really dynamic field, and we've got the potential to give rise to next generation photovoltaic materials that are lightweight, that are flexible, that are based on earth-abundant carbon, and that are very easily manufactured in a simple roll-to-roll production process. Now, previously the main drawback of these was their low efficiency, and as you can see, I've cited a couple articles that have PCEs of organic materials, polymer solar cells above 10%, and so these are all recent articles, and that show a couple things. One, development in polymer solar cells is still ongoing. We're still gaining large increases in conversion efficiencies, and hopefully soon we can reach the point where they will actually be competitive with inorganic materials and reach similar PCEs to the inorganic materials that are currently worked with. There's still much engineering work to be done, however, not only in the synthesis of new polymer semiconductors, but also the optimization of the synthesis of those components so that they use the fewest number of steps and use the fewest harmful reagents as possible. And finally, there's engineering work to be done on the encapsulation of these solar cells so that they're protected from environmental hazards like air and moisture, which would just defeat the lifetime of these solar cells. So, but it's my hope that researchers in the field will be able to get solar cells in the future that are similar efficiency as the current available materials and have similar lifetimes and are similar costs to the current generation of inorganic technologies. I'd like to thank everyone listening for your attention, and once again, thank you to the EEC for providing me the opportunity to give this presentation. I'd like to turn the floor back over to Scott Oakley and at the EEC, and I'd be happy to answer any questions that have been asked during this time. Thank you once again for your attention.
Thank you very much for your presentation, Alex. It was very interesting, particularly hearing about your research group's work at the University of Chicago. So, before we begin with questions, if any participants would like the European Energy Centre to send you the certificate of participation from this webinar, which you may need for your CPD or Energy CPD hours, please email the EEC on training@euenergycentre.org, stating your full name and the correct code, which will be given out in a moment on Paolo's slide. When contacting the EEC, you will be asked for this code in order to receive the certificate of participation for this training webinar. The code is EEC Organic 1, which you will be able to see on Paolo's final slide now. So going on to the questions, some of you have submitted some questions for Alex for this Q&A session, and the first one is, could you provide a brief summary of a few of the main benefits associated with organic photovoltaic cells, Alex?
Yes, so the main benefits, let's see. The main benefits are the small amount of material used. So we use, similar to current thin film, inorganic thin film technologies, we only use 100 nanometers of thickness in our active layer of the solar cell. So that's 100 nanometers is very, very small. That's not a lot of material. And this is similar to inorganic thin films that also use about 100 nanometers, but our thin films of polymers are carbon-based. And so we think in the long run, in the future, that will be cheaper and greener than rare elements like cadmium, tellurium, and rare metals like that. So it's not a lot of material with a thin film. Because of that, it's flexible. And in addition to that, because these polymers can be dissolved, the fabrication process of the solar cells is very simple. So by making these polymers and dissolving them, you can essentially just paint a solar cell onto. You can just make a solar cell basically with inkjet printer, pretty much. It's the same technology. You're just creating a film with something like a printer, basically. So that's very powerful in that you would have to spend much less setting up your polymer thin film factory, for instance, than you would to set up a similar factory to make inorganic thin films. And so that's the main event. Those are some of the main advantages to this technology.
That's great, thanks Alex. A nice follow-up to that question is from another participant. Why are organic solar cells able to be so thin?
Excuse me, what was that? Why are organic solar cells what?
Able to be so thin.
Why are they able to be so thin? How thin a solar cell can be made depends on how absorbent the material is. So if material is very good at absorbing light, you don't need a lot of it to absorb the light that hits the device. And so inorganic thin films and polymer thin films can both be made so thin because they're very absorbent. So pretty much as soon as light hits the solar cell, it will be absorbed. And this is in contrast to crystalline silicon. So crystalline silicon isn't that absorbent, so that's why it needs to be much thicker, because when the light travels farther through the cell, there's a larger chance of it being absorbed in the crystalline silicon. So yeah, it's how absorbent the materials are.
That's great, thanks again. Another question from one of the participants is, how close are organic solar cells to becoming commercially viable?
That's a tough question. I'm not completely sure myself, especially since the inorganic technologies are becoming cheaper and cheaper. So the more we improve, the more crystalline silicon and inorganic thin films improve as well. So whenever we reach a milestone, we suddenly need to pass another milestone before it's commercially viable. But I think if solar cells, if these polymer solar cells keep increasing at a similar rate, I mean, hopefully in the next decade or so, we might be able to see some polymer solar cells come to market, but I'm really not sure. I wish I could be more specific.
Well, that's great, thanks. I imagine that's quite a tough question to answer. So another question is, how easy will it be to upscale organic solar cells to large area devices?
Okay.
That's in comparison to inorganic cells.
So that is a very good question. So these the difficulty in organic solar cells in contrast to inorganic solar cells is in the initial fabrication. Not like I said, the actual forming the organic material into the solar cell is very simple, but it's a lot of steps before you get the material to make the material you want, as opposed to something like silicon or gallium or copper indium gallium selenide. These are relatively simple to make, but hard to fabricate into a solar cell. So yes, this fabrication of these solar cells uses some toxic reagents, and I mean, what I personally do wouldn't be, you couldn't directly scale it up to actual production plant scale, but there are groups working. I can think of some groups at University of Southern California and a couple people in Japan off the top of my head who are working to eliminate the worst reactions from the fabrication process. So at the same time we're trying to develop better materials, people are working on ways to make those materials in a greener fashion. But that's a very good question. Thank you.
Thanks again, Alex, for taking the time to answer those questions. And thank you everyone for submitting your questions as well. But I'm afraid that's all we have time for. I will now hand over to Paolo once more to conclude the webinar.
Thank you very much, Alex, for your presentation and for your time. The presentation was extremely interesting, and obviously we received extremely interesting questions as well. So thank you also to all involved in the realization of this webinar. A special thank you goes to the very many participants connected live from all over the world. We actually have representatives from Europe, Africa, Asia, of course America, all currently connected live now to this training webinar. So to keep up to date with upcoming webinars, please visit our website, euenergycenter.org. To register on any of the courses, of course, please visit www.euenergycenter.org/training for classroom courses and www.academy-eec.co.uk for distance learning courses. You can find the URL links also shown now on my slide. So thank you again. I look forward to seeing you soon on our next training webinar, Seminar for Distance Learning Courses. So from all of us here at the EEC office in Edinburgh, United Kingdom, and from Alex from the University of Chicago in the US, thank you and goodbye for now.